Okay, so welcome to the second part of Chapter 6, where we're going to move into molecular orbital theory. But before we do, let's just do a quick review of valence bond theory. So valence bond theory does a better job of predicting many properties about a bond between two atoms. It does a better job than Lewis theory, but it does have some shortcomings. So, for example, it can't predict magnetic behavior and or some other qualities that exist when we look at the reality of how atoms come together. And one of the big shortcomings of the valence bond theory is this down here, in that it presumes that electrons are localized in orbitals of atoms in the molecule, and it doesn't account for something known as delocalization. What do I mean by that? Well, let's take a look at that. So in valence bond theory, what we have is the concept that the electrons are located in a specific orbital around the nucleus, and that in order for a bond to occur, there has to be some sort of manipulation of that orbital, a change in shape and a lowering of the energy state in order for there to be some sort of a union that occurs with another element. So we would have our very nice and tight ground state orbital that goes from something that looks like this to maybe something that looks a little bit more like that, so that it can create a union with some other atom. Now, in order for this to be the case, the thing that you kind of have to presume is that all orbitals exist in a distinct place around a nucleus, and the reality is that's not the case. The other thing is that you have to assume that at any given moment all the electrons are available all the time to form unions, and that's not a reality either. So molecular orbital theory takes into consideration that there are times when an electron may not be available to form a union, and that is and valence bond theory doesn't, and that tends to be one of the shortcomings. So let's take a look at molecular orbital theory. Molecular orbital theory has its basis in the work of Schrödinger and his four quantum numbers: the principal number, which tells us about our orbit, our angular momentum, which gives us some idea about our suborbitals, our magnetic number, and our spin. So those are the four numbers. And when you run calculations, or when Schrödinger ran the calculations, what he came up with is a wave function that predicts the likelihood of where you're going to find an electron in any given suborbital. And the way that we can predict it is like this, is that the area where there's a big peak or dip, strong likelihood of finding an electron when we're in this region. When we're in this area of the phase, our chances of encountering an electron are pretty small. Same thing as over here at this end. And when we hit this area where we go to the line, and we're crossing the line, I guess, going up or going down, likelihood of finding an electron there drops to 0. So the areas where we have some fullness in our wave function, this is known as the antinode. Antinode is when we have electron availability. And the regions where that drops to 0 are called the nodes. Now, why is this antinode and node business important? Well, let's say that we were an atom and we were looking to have our electrons create a covalent bond with an approaching atom. As long as the approaching atom's electrons were in a very similar phase as our own electrons, we might create a union. Because look, my electrons at this point in time are very available, and the incoming electrons of the incoming atom, are also equally available, and the likelihood that some sort of a union could be created is pretty strong. But let's say that the incoming atom had electrons that were slightly out of phase, like here. Well, that means that when my electrons were available to bond, the electrons of the incoming atom weren't, and the likelihood of a union forming in that instant drops to kind of like 0. So there is this accounting method known as the linear combination of atomic orbitals that helps us predict the likelihood of a union forming between two atoms. And we're going to look at this in a little bit more detail. This picture probably doesn't mean much to you right now, but it's basically trying to tell you that when the electrons are aligned in phases that are complementary, you're going to end up creating a union, and you will end up having what's known as a bonding orbital. If the electrons are not aligned in such a way that they can form a union, what you end up with is something known as an anti-bonding orbital. So there's a likelihood that you can have bonding orbital. There's also a likelihood that you can have an anti-bonding orbital. And the way that this is explained, because what we're dealing with are sine waves, is through the concept of constructive or destructive interference. So when the waves combine constructively, we're going to end up creating a bonding orbital. When the waves combine destructively, and that's a possibility, we're going to end up creating an anti-bonding orbital. So when we have the creation of a bonding molecular orbital, what essentially has happened is we have constructive phases of our waves between our electrons, and basically we're going to be able to find the electrons located somewhere between the nuclei of the two atoms that are trying to create a union. When we have an anti-bonding scenario, what's going to happen is we're going to be out of phase. We're going to have that destructive interference in our sine waves. And we're going to find the electrons outside of the internuclear axis. That means that the electrons are going to be found on the outside of the area that exists between the two nuclei. So my explanation is this. You have a couple of atoms that are trying to come together. There's the electrons, and if we look at where these electrons are located, they're located between the two nuclei on the inside region of the two approaching nuclei of the atoms. And this is our bonding molecular orbital. There's a bond that's going to form in this scenario. If we have the other scenario, where the electrons are on the opposite side of the nuclei of the two approaching atoms, I mean, we can tell just by this example that the likelihood of these two atoms, these two electrons in this moment creating a union are kind of nil because they're not close to each other. And this is the scenario when we have the anti-bonding molecular orbital. So this is the image again from the book that says that when you have destructive interference, you're going to end up creating the anti-bonding molecular orbital, and there's not going to be any sort of a covalent bond formed. And when you have constructive interference, that is when the nodes line up, you're going to end up creating that bonding molecular orbital. Now, if we give this some language, we can say that electrons in bonding molecular orbitals are stabilizing, and they're going to have lower energy, which is what's going to lead to that covalent bond. Now, electrons in anti-bonding molecular orbitals are generally said to be destabilizing. They're higher energy. The electron density is going to be outside of the internuclear axis. That means that they're going to be on opposite sides of the nuclei in their orbitals in that moment of their orbitals. And as a result, the anti-bonding orbitals are going to cancel any stability gained by electrons that are in bonding orbitals. So because this is all kind of fluid and dynamic, what the molecular orbital theory says is that we need to take into consideration the likelihood of a union forming, as well as the likelihood of a union not forming. And the reason why is because mathematically both exist. So this is the beauty of molecular orbital theory. Now, valence bond theory and molecular orbital theory are basically elaborate accounting systems that help us predict the likelihood of where we're going to find an electron, or maybe some other component of its behavior. With molecular orbital theory, what we're going to be looking at is something known as bond order. And bond order, if you look down at the bottom of this slide in red, is defined as the number of bonding electrons minus the number of antibonding electrons divided by 2. Now here's the deal with bonding, with a bond order. The bond order is going to be calculated based only on the valence electrons. We don't need to take into consideration all the electrons, just the ones in the outer orbital. This number may be a fraction in order to predict the likelihood of a union forming between two atoms. The higher the bond order number, the stronger the bond between the two atoms, and the shorter the bond between two atoms. And if a bond order is equal to 0, or if it's even less than 0, which I don't think can happen, can it happen? I think it can happen. It seems like I've done a calculation where that's the case. Anyway, if it's equal to 0, then the bond is unstable and no bond will form. So doing the calculation of counting and the number of bonding electrons and anti-bonding electrons and then dividing them by 2 gives us an indicator of whether or not we're going to have a union form. And this is a really powerful tool to have, because it can help us predict some things where Lewis falls short and valence also short. Valence bond theory also falls short. So when we're trying to do the calculation for the bond order, this is the sort of chart that we're going to use. And what you see is we have an increasing energy indicator over here. And because what we're trying to do is compare the likelihood of the union between two atoms, we're going to list our atoms out here off to the side. And when we combine their electrons, we're going to do that here in the middle. We're in a molecular orbital. And we're going to start by filling in the bonding electrons first, because they are lower energy. And then if we have electrons left over, we'll start dropping them into the anti-bonding orbitals. So let's work through this. So our question is, can we have a hydrogen molecule that is a union between two hydrogen atoms? Well, we know that. We know that that's true, but let's go ahead and work it out. So in order to do this, we need to know the number of electrons that we have. Well, each hydrogen is going to have one electron. And since we're trying to combine two hydrogens, each one is going to bring to the table one electron. So we've got 2 electrons that we need to place in our chart. So we could say that each hydrogen atom brings an electron. So the hydrogen atom to the left brings 1 electron. Hydrogen atom to our right brings 1 electron. And in order to create the hydrogen molecule, we're going to drop these 2 electrons in the bonding orbital first. And since we only have 2 electrons to find homes for, that's all we have to do. Now let's do our bond order calculation. So remember, this is the number of bonding electrons, which in this case is 2. And we're going to subtract the number of anti-bonding electrons, which in this case is 0. So when we do this, we do the math. 2 minus 0 is 2. Going to divide it by 2. And it ends up being 1. And yes, we can predict that the hydrogen molecule exists. So let's see if we can predict the existence of a helium molecule, that is a union between 2 helium atoms. Well, each helium atom is going to bring to the table 2 electrons. And since we have 2 atoms that we're trying to combine, we're going to have 2 atoms with their 2 electrons bringing to the table 4 electrons total. So we're going to fill in helium to the left with its 2 electrons, helium to the right with its 2 electrons, and then start filling in our chart with our bonding and our anti-bonding electrons. So 2 of our 4 electrons are going to go in the bonding orbital, and 2 of our electrons are going to go in the anti-bonding orbital. And then when we do the math, That is, take the number of bonding electrons, subtract the number of anti-bonding electrons, and divide it by 2, we end up getting 0. And indeed, we understand that because hydrogen has a full valence electron, a full valence orbital, it's not likely to create a union because it has no need to share electrons with anybody. So what about a polyatomic helium ion? Could that exist? Well, let's take a look. We know that each helium could bring to the table 2 electrons, but because we have that positive up there, that means we've lost an electron. So now we have 3 electrons to find homes for. So let's drop in our electrons. We've got our helium atom off to the right. It will have 2 electrons. And our helium ion to the, I think I said helium atom to the left, helium ion to the right, it will have 1 electron. That means we're going to find homes for 3 electrons. 2 of them are going to be placed in the bonding orbital, and only 1 is going to make it into an anti-bonding orbital. And if we do the math, which is to subtract the bonding electrons, the anti-bonding electrons from our bonding electrons, we're going to end up with a bond order of 1/2. So yeah, it is a possibility that this ion would exist. So we were looking at hydrogen and helium who have only 1 orbital. What if we have elements from the second period where we're now looking at a full first orbital and we're moving into a second orbital? Well, lithium's a good example of that. Lithium only has 1 valence electron, and we would run the scenario with lithium that looks very much like what we see here. The exception being that now we're saying right here that our valence electrons are located in the 2s subshell, 2s subshell. And when we start filling in the bonding and anti-bonding electrons, we're going to have a sigma 2s and an anti-sigma 2s. The same thing is true for beryllium. If we look at beryllium, who's the neighbor right next door to lithium, we're going to be looking at a 2s and a 2s and a sigma 2s and an anti-sigma 2s. So what about p orbitals? What's happening with the p orbitals? Well, this is your shape of p orbital, and in this case we're looking at 2p of x. So keep in mind these guys are going in what is that, an infinity sign, sort of an orbital, and so it is likely that we're going to run into that scenario where we have bonding and anti-bonding molecular orbitals. So we can, yeah, there's your central atom. So we could have them either clustered on the inside approximation inside of the nuclei or on the outside of the nuclei. So we would have the same sort of a scenario that we had with an s orbital, where we could end up having our 2 electrons in the anti-bonding position, that is on opposite sides of our nuclei, of our 2 atoms that are trying to create a union, or we could have them on the inside of the nuclei of our atoms that are trying to create a union. So it's the same scenario, it's just now we're looking at p orbitals. So this is what the molecular orbital chart is going to look like for our atoms that have valence electrons in a p orbital. So you would see that we've expanded and we have a p orbital that we have to fill out over here. If we look and see who our players are, down here we have boron, carbon, and nitrogen. And on the right side of our energy diagram we have oxygen, fluorine, and neon. Now why do we have this line and 2 different charts? Well, the reason why is this right here. If you look at what's happening on the elements on the left of the energy diagram, our alpha orbital is lower energy than our sigma in the p orbitals. And then on this side of the energy diagram, the sigma is lower energy than the pi. So if you're dealing with atoms of boron, carbon, and nitrogen, you're going to have to use this configuration. And if you're dealing with these players, oxygen, fluorine, and neon, you're going to have to be mindful to deal with this configuration. Now, because we're dealing with valence electrons that are located in the s orbital as well as the p orbital, we have to fill out this s diagram as well as this p diagram and all that's involved with that as far as bonding and anti-bonding.
All right, so let's work a problem using this chart that has the p orbitals on it. So we're posed with the question, can we have a diatomic carbon with a positive charge exist? Well, let's run the numbers and see. So we know that each carbon is going to bring 4 electrons. We have 2 carbons, so we're going to have 2 times 4. But then we have the influence of that positive charge, which means we have to subtract an electron. So we have a total of 7 electrons that we're going to have to place in our chart. Let's designate the left side as our regular carbon. Regular carbon has 4 electrons in its valence orbital. 2 will be in the s subshell, and another 2 are going to be in the p. Now our second carbon, we're going to designate that as our cation, and it will have 2 electrons in its s subshell, but only 1 in its p. All right, coming down here to the bonding and anti-bonding sigma bonds, we've got 4 electrons that can go here. 2 will go in the bonding square and 2 will go in the anti-bonding square, and we're done with that. Now we've got 3 electrons that we have to place in our p orbital chart. And we're going to start down at the bottom because we want to start with the lowest energy. So we're going to drop a couple here, and we're going to drop that third one right there. Now I know that should have been kids on the bus. We should have filled the 2 ups and then the down. I get that. But I'd have to stop the slide and redo the animation, and I'm done. I've recorded this slide like 4 times now, so I'm done recording this slide. This works. Okay, let's figure out what the bond order is here and what it looks like. So we've got bonding electrons here and some more up here in the p, and then we have just these 2 anti-bonding. So our bond order, we're going to have to count our bonding electrons. We've got 5 of them. We've got 2 anti-bonding electrons. If we drop that in our formula, which is 5 minus 2 over 2, then we end up with 3 over 2. Even though it's a fraction, it is greater than 0. So yes, our positively charged diatomic carbon molecule can in fact exist. What if we have the same molecule except now we have a negative charge? Well, let's run the chart and see what it looks like. So we have 2 carbons, each one bringing 4 valence electrons, and 2 times 4 plus an extra one because we have that negative charge up there. So now we have 9 electrons to find homes for. So let's designate the chart off to the left as our regular carbon, 2 electrons in its s orbital, 2 in its p. The carbon off to our right is going to be our anion version of our carbon, 2 electrons in the s orbital and 3 electrons in the p. Now let's start filling in our chart. So we've got in the sigma bonds, we've got 2 bonding electrons, 2 anti-bonding electrons, and now we've got to place 5 electrons in the chart in the p orbital. So we're going to place a couple here and a couple there. I know, kids on the bus, I know, again, I'd have to change it, and I'm not going to. So we place 4 of our 5, and there's number 5. All right, let's figure out what the bonding order is by identifying our bonding electrons and our anti-bonding electrons and plug them in to our little chart over here. So we have 7 bonding electrons, 7, yes, and we have 2 anti-bonding electrons, and we plug that into our formula, and we end up with 5 over 2. So yeah, this version of a diatomic carbon with a charge on it can exist as well. All right, that's fabulous. Well, what about this question? Which one is more stable? The double carbon with the positive charge or the double carbon with the negative charge? Can we make that determination? Why, yes, we can. And we can do that because we know about bond order. And the rule about bond order says that the larger the bond order, the stronger the bond and the shorter the bond, which means it's got a pretty strong bond as well. So if we take a look at our numbers here, our bond orders, we have 5/2 from our negatively charged ion being greater than 3/2 of our positively charged ion. So we could then conclude that carbon, the double carbon with the negative charge, is the more stable version. So here's a nice summarization of the molecular orbital theory and the utilization of the linear combination of atomic orbital chart that we've been using. The first point says that molecular orbitals are a linear combination of atomic orbitals. Basically that says that, yeah, we know we're counting up the electrons and we're dropping them in a chart. The second bullet says when two atomic orbitals combine to form two molecular orbitals, one molecular orbital is lower in energy and the other is higher in energy. And this is kind of the universal law that says if you have two of something, you're going to compare them. So one is always going to be bigger in something than the other one. So yeah, no surprise there. The third bullet says when assigning the electrons of a molecule to the molecular orbitals, we fill the lowest energy molecular orbitals first, and with a maximum of 2 spin-paired electrons per orbital. That says that, first of all, we understand that Mother Nature, although she's a drama queen, has a tendency to be a little lazy, and we're going to lean towards those low energy systems before we lean towards a high energy system. And that also we understand the Pauli exclusion principle, which says we can only have 2 electrons per atomic orbital. The fourth bullet says when assigning electrons to 2 molecular orbitals of the same energy, Hund's rule is followed to fill the orbital singly first and with paired spins before actually pairing them. That's the kids on the bus rule that says you should fill the up spins first and then the down spins. The thing that I didn't do because I didn't want to go back and fix the animations in my PowerPoint. And then the fourth thing, or the last bullet says the bond order in a diatomic molecule is the number of electrons in bonding molecular orbitals minus the number of anti-bonding molecular orbitals divided by 2. That's our formula that we're using to calculate that bond order and figure out whether or not we have a stable union between 2 atoms. So far, we have been combining atoms that were the same, like a couple of carbons, a couple of hydrogens. What happens if the atoms that we try to combine are not the same? Well, we would say that they were heteronuclear diatomic molecules or ions. And here are some rules about them. So the first one says that when combining atomic orbitals are identical and of equal energy, the combination of each atomic orbital to the molecular orbital is equal. Basically, the same is the same. So there's no real earth-shattering news with that. When combining atomic orbitals that are different types and energies, the atomic orbital closest in energy to the molecular orbital contributes more to the molecular orbital. So this is getting into a level of detail about who is contributing the most. And it has to do with having some understanding of the energy levels that the electrons are existing in for each atom. And we'll take a look at that in the next couple of slides. Here's an interesting rule. The more electronegative an atom is, the lower in energy are its orbitals. So that's now starting to give us a little bit of explanation to the second bullet. How can we make a determination about who is higher energy than and who is the lower energy contributor? Lower energy atomic orbitals contribute more to the bonding molecular orbitals because they're lower energy. They would contribute to the bonding orbitals. Higher energy atomic orbitals contribute more to the anti-bonding molecular orbitals. That's kind of repeating what we've already been saying in these past few slides. And non-bonding molecular orbitals remain localized on the atom donating its atomic orbitals. Yes, that's true. And we'll be looking at these in the next couple of slides and giving these a little bit more of an explanation. Okay, let's say that we were going to try to do the chart for nitrogen monoxide. The first thing you might notice if you look at the p orbitals is that the order that we're filling the p orbitals is the sigma and then the pi. And if you look back at one of your charts, you'll see that the diagram that we're using is specific for oxygen. Now, why are we using the one specific for oxygen and not for nitrogen? Well, let me explain. If we were to bring up the electron diagram for nitrogen, it comes in about like this. Nitrogen has 5 electrons in its valence orbital, and 2 of them are going to be in the 2s, and the other 3 are going to be in the 2p. If we bring in the same for oxygen, they come in at the lower energy level. So we're going to be using, and that's the reason why we're going to be using this the chart for oxygen as opposed to the chart for nitrogen, because if we were trying to combine nitrogen with something that had higher energy than it, then we would use the chart for nitrogen. But because we're combining nitrogen and oxygen having the lower potential energy, we're going to be using the chart for oxygen. All right, so if we start by looking at what we have to fill, let's just look at the s orbitals. We have a total of 4 electrons that can start to fill up those s orbitals in our chart. So we put a couple in the bonding orbital and then a couple in the anti-bonding orbital, and we're done with that. Now let's look at our p orbital. Nitrogen is going to contribute 3 electrons. Oxygen contributes 4 for a total of 7 electrons that we have to place. So we're going to put a couple in the sigma bonding orbital, and then we're going to put another 4 in the pi bonding orbital, and then our next lowest energy orbital that we're going to put something in is going to be the pi anti-bonding. So we're going to put that one remaining electron in the pi anti-bonding orbital. So it's just as simple as figuring out how many electrons you have and dropping them in the orbitals, following the Pauli exclusion principle, where you only put 2 per square, and the Hund's rule, which is kids on the bus, fill singly and then doubly. Now, what is the bond order for this molecule? Well, we can figure that out. The first thing we need to do is identify our bonding and our anti-bonding electrons. So we have 3 bonding orbitals that have something in them, and we have 2, 4, 6, 8 electrons in bonding orbitals, or we have 8 bonding electrons. And how many anti-bonding electrons do we have? Well, we have 3. So if we drop these numbers into our equation, 8 minus 3 over 2 gives us 5 over 2, or 2.5. So that is the bond order for our nitrogen monoxide. And this brings us to the conclusion of Chapter 6. So yes, Chapter 6 really is about the valence bond theory and molecular orbital theory and those 2 major topics. All right, well, thanks for watching.